Hello there, Mr. Sutton here, bringing you the Algebra 2 6-1 lesson on exponential growth and decay functions. This will be a two-parter, and specifically in this one, we're going to be identifying, graphing, and writing exponential growth and decay functions in a variety of real-life situations. So we're going to do a deep dive into exponential functions and find out what these are all about. First, let's define them. We have lots of functions that we've seen that have exponents in them, but they're not all exponential functions. An exponential function is one that has a variable in the exponent, not a constant. Because you have your exponent changing depending on the x values that you're plugging in, that means that you're going to be multiplying by more and more copies of the same number. So we actually have a repeated multiplication going on here. Versus a linear function where you have repeated addition. So it's kind of the same idea, different operation. The standard form of these exponential functions is y equals a times b to the x. And it's important to note that this x here only applies to this b value. The a value is just something that gets multiplied after the fact because exponents happen before multiplication. Now the x and the y are the only true variables. In one of these, the a and the b will actually both be constant numbers that are filled in with values on a specific problem. And there's only certain numbers that we're allowed to use to call this an exponential function. A and b both have to be greater than 0. If either one of these is 0, then this whole thing would just be y equals 0, which would just be a line, not an exponential function. And if we had negatives here, we just kind of agree as mathematicians not to have negative a values, but the b values would be a huge problem because then you'd have a negative being raised to even, odd exponents and just kind of flipping all over the place in terms of where it was. We also have a stipulation that b should not equal 1 because if you have 1 to any power, that's just going to be 1 and you're just going to end up with y equals whatever the a value is. So that's not very interesting either. So with all this in mind, here is a sample function for us to play with, y equals 1 times 2 to the x. Now typically this 1 out here would not even be written, it would be an invisible 1 rather, but we're just going to put it in there just because this is our first example. What I would like you to do is pause the video and using this table here of values from -2 to 2, which is what we typically use when we graph one of these with a table, plug all those in, get some y values, plot them in, and see what this thing looks like. All right, so plugging in each of our x values, we have 1 times 2 to the -2. This 1 out in front, let's just agree right away, that's not doing anything for us, so we'll just kind of ignore it. But 2 to the -2, that's really 1 over 2 to the +2, or 1 over 4. Next, we have 2 to the -1, which is just 1 over 2. Then we have 2 to the 0. Anything to the 0 is 1. And then 2 to the 1 is 2. And before we do the last one, have you noticed a pattern here? These are being all multiplied by another 2 to get the next value. So if you have the first value and these x values are just going by 1s, you can just keep multiplying by whatever your b value is to get the next y value. So it's kind of nice like that. But then we have 2 times 2 giving us 4. All right, let's graph all these. So we have -2, 1/4. We have -1, 1/2, 0, 1, 1, 2, and 2, 4. And we could keep going. I mean, you've got 8, 16, 32. You just keep going. This is getting steeper and steeper as you go. And going the other direction, you could divide by 2 to get values going the other way. So 1/8, 1/16, 1/32. So this is going to look kind of like this. So here's our basic exponential curve. Now you might be wondering what happens if we keep going further and further left. Does this eventually touch and or cross the x-axis? Well, we'll get back to that question. For now, there's a few key features I wanted to point out on this graph. One of these is we have a y-intercept here of 1, and you can actually pick that right out of the original function. You're going to get a y-intercept where your x value is 0, and if you have an x value of 0, that's going to turn your b value into a 1, because anything to the 0 is 1. So you're just going to end up with this a value times 1, which means your a value is going to end up being your y-intercept. Now you didn't really need to know that in order to graph this, But it is kind of nice to know when we start doing word problems and we have initial values to know that those initial values, those starter values of the real life problem, are this a value here. Now this b value, we need to give that some justice as well here. The b value has a special name. Because you're multiplying by it over and over again, it's a factor. And depending on what type of b value is, it can either be the growth factor or the decay factor of the exponential function. If the b is bigger than 1, so that you're multiplying by numbers that make your overall result go bigger and bigger. If b is larger than 1, then this is called a growth factor. If, on the other hand, b is between 0 and 1, I don't want to say less than 1 because I don't want to include negative numbers. They said we're not supposed to. But if b is between 0 and 1, like say 1/2, then you're going to be multiplying by something less than 1 over and over. It's going to make all your numbers smaller and smaller. So in that case, we end up with what is called a decay factor. Now, earlier on, we asked what happens as this graph goes further and further and further to the left. I think we can assume as we go further to the right that this thing is going to positive infinity. But how about to the left? So it turns out that since you are starting with a positive factor, and you're either multiplying over and over or dividing over and over, depending on which way you go with your numbers, with a positive number, the only results you can get are also going to be positive numbers. You can't get 0 because you're never multiplying at any point by 0. And you can't get a negative because you're not multiplying by a negative. So the output is always going to be positive, greater than 0 for a true exponential function. This means that you're going to get something called an asymptote in the graph. An asymptote is a line that your graph keeps approaching. It gets closer and closer and closer. Sometimes it might actually cross over it back and forth. Sometimes it never touches it. It kind of depends on the situation. In this case, it's never going to touch the x-axis because you can never get to a value of absolute 0 with this thing. But in general, these exponential functions we're going to find, they all have asymptotes at the line y equals 0, at the x-axis. Later on, when we do rational functions, we're going to see some other function families that also have asymptotes, albeit for different reasons. So here is another exponential function. Using what you learned on the last one, see if you can figure out whether this is exponential growth or decay, and then graph it out. Pause the video, give it a shot. All right, so let's start with the growth versus decay thing. Since this b value right here, we have an invisible a value of 1. Since the b value is between 0 and 1, that tells us that this is going to be exponential decay. So as we move to the right, we expect our graph is going to be going down rather than up. The value should be getting smaller. So let's do our table now, again using values from -2 to 2. So we plug all of these values in. Let's start with 1/2 to the -2. That's really 2 over 1 to the +2. Negative means reciprocal. So that actually ends up being 4. And then 1/2 to the -1 is going to be 2. And we've got anything to the 0 is 1. And you see here what we're doing is we're just multiplying by 1/2 each time. So 1/2 times 1 is 1/2. 1/2 times 1/2 is 1/4, and you could keep going to get 1/8, 1/16, all of those. So here's our graph for all this. We have -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, and we know from before that we never actually get to the x-axis. We just keep getting closer and closer. So we start up here, and we've got this nice little horizontal asymptote going toward the x-axis. So up to this point, we've encountered some growth factors and some decay factors, but in a real-life setting, very rarely do we actually have factors handed to us. More often than not, they are expressed as growth and decay rates. So this is a little bit different than a factor. A rate is like, something is decaying at a rate of 3%. So we might be wondering, well, how does this translate into the growth factor itself? So if we know the growth or decay rate, which we're going to call R from this point onwards, we can actually use the following forms to fit this into what we already have for our exponential model. So instead of writing a times b to the x, we can write a times, instead of b, we can write 1 plus r. And instead of x, we're typically going to use t for a lot of these real life problems because that models time. And if we have exponential decay, then instead of doing 1 plus r in here, we're going to have 1 minus r. That's the only real difference, though. So kind of the intuition behind what's happening is if, for example, you want to increase something by 5%, then you have to multiply it by 1.05. The way you would get that out of this is you would turn your percentage of 5 into 0.05, add it to 1, and abracadabra, instant growth factor. If you wanted to decrease by 5%, well, then you'd need to do 1 minus 0.05, and then you'd be multiplying by 0.95. You'd be getting 95% of something. So that's what's going on with this form. Now later on, we're going to actually use this form to write exponential functions if we know the growth or decay rate. But for now, we're actually going to go the opposite direction. They're going to give us an exponential function, and we're going to see if we can work backwards to figure out what the growth or decay rate was, because that also might be nice to know. So here is our problem to try this out on. Let's say that the amount y in grams of the radioactive isotope chromium-51, whatever that is, remaining after 10 days, or t days rather, is given by y equals a times 0.5 to the t over 28. And then a is the initial amount. There's that y-intercept again, the initial amount in grams. They want to know the percentage of chromium-51 decaying every day. So ultimately, in order to figure out the decay rate, we want to rewrite this formula here, which is in something called half-life form, which we're not going to worry about right now. We want to rewrite this in either exponential growth or exponential decay form. Probably decay because they're talking about decay. In order to do that, though, we need to first put this in just regular ab to the t form, standard form. So that'll actually be our first step here. So to find r, we're going to use some exponent rules and rewrite this in ab to the t form. So what exponent rules specifically? Well, instead of writing this as 0.5 to the t over 28, I could think of this as like t times 1 over 28. And if I wanted to, I could move that 1 over 28 inside the parentheses with the 0.5, like so. And if you're a little bit skeptical about this, just remember our exponent rules. If I raise a power to another power, I just multiply the powers, right? So this would go right back to being t over 28. Well, I can unmultiply exponents in this fashion as well, and that's what I have to do here. So what is actually 0.5 to the 1 over 28? For that, I'm going to consult Desmos. So here's my Desmos calculator. Let me do 0.5. I probably don't need the parentheses. Exponent, and we'll do 1 divided by 28, and that comes out to, I'm going to want to take it out to 4 decimal places probably, so 0.9755 and some change. So that 0.9755, that is the actual b value in ab to the t form here. The a value we don't know, and we actually don't need to know to do this problem. Next step we have to do is we need to convert this b value into either a 1 plus r or a 1 minus r. We need to rewrite this as 1 plus a number or 1 minus a number. And whatever that number is that we're plussing or minusing, that's going to end up being the decimal version of our decay rate. So with this in mind, pause the video and see if you can take this the rest of the way. Alright, so if we're choosing between these two forms, since this is a number that's less than 1, we probably want to rewrite this as 1 minus some decimal. So what do I have to subtract from 1 to get 0.9755? I don't know, but I bet Desmos does. So let me just clear all this out here, and let me do 1 minus 0.9755, and it looks like I would have to do 1 minus 0.0245 to get this 9755. So that's what I'm going to rewrite this as, 1 minus 0.0245. Since this is what I'm subtracting, this whole decimal here is going to be this r. So that means that my decay rate is going to be the percentage version of this, which means I just have to move my decimal 2 spaces to the right, and this ends up being 2.45% for my decay rate. So at this point, we're going to get a little more practice with finding growth and decay rates. This time around, the problem is specifically worded to tell you to rewrite this in either growth form or decay form, state the rate, and then describe the end behavior. You can figure out the rate after I tell you to pause the video in a moment. We will figure out the end behavior together after you get the actual rate. So pause the video and give that part of it a shot. All right, so just like before, we're going to use our exponent rules to make this into a times b to the t kind of form. To do that, we need t to be alone in the exponent. So this 1/3 needs to move inside with the 2. And then if I go ahead on Desmos and raise 2 to the 1/3, like so, then I end up with about 1.2599. So that's my b value. I'm going to be rewriting this using this 1 plus r format because this is bigger than 1, so I can just rewrite this as 1 plus 0.2599. It's a little bit easier than when it's less than 1 and I have to figure out what I need to subtract. So this means that my r value is 0.2599, which means that this is 25.99%. And since it's 1 plus that, this is a growth rate of 25.99%. All right, so this next part here about the end behavior, we're basically asking as x approaches negative infinity and positive infinity as we move to the far left and the far right, what's the y value doing? And this is a pretty straightforward one if you remember the shape of our two exponential models. Remember that with growth, we started near 0 and veered off into positive infinity. With decay, we started at infinity and leveled out at 0. So you just need to know which shape we're dealing with, and then that'll tell you what your function's doing. So for example, on this one, as x approaches negative infinity, since this is growth, since we start near 0, that means that y is approaching 0 as you move to the left. And since this is, again, growth, and we're going to infinity as we move further to the right, that means as x approaches infinity, y is also approaching infinity. So this concludes part 1 of this lesson. Pause the video, get a little bit of practice with graphing and growth rates and all that kind of stuff, and then come back and we'll actually use this form to figure out how to write some exponential real-life functions. See you then. Welcome back to part 2 of this lesson. We're going to start right in with a exponential application. That's a really cool looking car. Let's say the value of a car, probably not this car, can be approximated by the model y equals 25 times 0.85 to the t. And t is the number of years since the car was purchased. So there's a few things that we're going to ask you to do here, some of which you did in the last part, so this is just sort of a warm-up. First off, determine whether the model represents growth or decay. We've already kind of done that, so you can give that a shot in a moment. And then also identify the annual percent increase or decrease in value of the car, basically just asking for the growth or decay rate. Again, that's kind of old news. Here's something that's a little bit new, though. They want us to estimate when the value of the car will be 8,000. So this is something we're basically asking, when will this function give you an output of $8,000? Now, it is important to note that this function is already expressed in thousands of dollars. So when you're deciding what to plug in for y, just be careful with what you plug in. When you get an equation by doing that, just as a little bit of a hint before I set you loose here, you can actually solve any equation by graphing each side of the equation on Desmos and just seeing where the two curves intersect. So pause the video and see what you can do with all of this, and we'll bring it back together. All right, let's start with part A. Is it growth or decay? Well, our b value is 0.85. Since that is between 0 and 1, that tells us this is decay. And this kind of makes sense if you know a little bit about cars. They tend to go down in value after they leave the lot, unless you've got one of those weird antique cars and somebody willing to pay for it. The next part, part B, identify the annual increase or decrease percent in the value of the car. Well, for that we need to rewrite this in that 1 minus r form. 0.85 can be rewritten as 1 minus 0.15. And if we rewrite it like this, we see that this is a 15% decay rate. So 15% decrease annually in the value of the car. Now how about this last part? So to estimate the value of the car at $8,000, we're going to have to use this equation, and if they want the output to be 8,000, and these y values are already expressed in thousands, that means we have to substitute 8 for y. And then we have to graph this on Desmos. So let's go ahead and do that now. So here's my good friend Desmos. Let's go ahead and graph the equation here. So we're going to graph y equals 8 as one of our graphs, and then we're going to go down and graph y equals 25 times 0.85 to the, I'll just make it x just to make Desmos. T would probably work, but let's use x just in case. And we just need to see where these intersect. So coming up here, let me just zoom out a little bit, make sure this is the only intersection point. Looks like it is. It seems that they intersect at this spot right here at the x value 7.01 and some change. So here's the graph that we just kind of looked at. I just zoomed in a little bit. So that means that our t value then is 7.01 years. So this is approximately how long it takes your car to decrease to a value of $8,000. For our next problem here, don't look so surprised, we're going to be writing and using an exponential function for this real-life situation. So in 2015, apparently, the world population was about 7.38 billion. That sounds like a lot. During the next 5 years, the population increased about 1.09% each year. Doesn't sound like a lot, but when you're doing that on a billion, it's a lot. They want us to write an exponential model that represents our population in billions t years after 2015. So that's going to be important. And then they want us to estimate the world population in 2020. Okay, so first step we want to do on these is we want to figure out, is this going to be growth or decay? And we're going to choose the growth or decay form based on that choice. Once you've done that, you're going to need to fill in some values, right? Because you have an A, you have an R, you have a T, you're going to need to fill in all of these things to figure out the population in 2020. The A value, remember, is just the y-intercept. So in real life terms, that's just going to be your starting value, whatever you initially had for your population. The R is going to be expressed as a decimal, so be careful plugging that in. And then for the T value, that's how many years have elapsed since the start value. So we've got to be careful with that as well. With all that in mind, I know I'm asking a lot here, but pause the video and see how far you can get on your own trying out this problem. All right, let's see how we did. Did you choose growth or decay? Well, they said the population was increasing, so the growth form, a times 1 plus r to the t, makes more sense than decay here. For the a value, we've got the initial population in 2015 of 7.38 billion, and since y is expressed in billions, we can just write 7.38 and we understand that that really means billions. Now for the r value, they gave us a percentage. Remember, we have to convert that into a decimal to plug it in for r. So we move the decimal to the left by 2. That gives us 1 plus 0.0109 to the t power. And if we want to be fancy, we can combine that with the 1, and there is a simplified exponential model for our world population. Now that we've got this, we can plug in whatever we want and figure out the population. But they want to know the population in 2020. Before you just kind of plug in 2020 or plug in 20, remember that this model applies to the number of years since 2015. So the t value to get 2020 is going to be 2020 minus 2015, or 5. So we have to do f of 5 in this case. So 7.38 times 1.0109 to the 5th power, which I'm not going to do in my head. Let me go to Desmos for that. So here we go. 7.38 times 1.0109, raise that to the 5th power, and that comes out to about 7.79, and that's going to be in billions of people. For our next problem, we're going to talk about money. We just talked about babies, basically. Well, at some point, those babies grow up and they want to go to college, or some of them do anyway. So you got to save up for that. Let's say you put $700 into an account to use for said school expenses, and the account is earning 10% interest. Maybe not so realistic for today's world, but I don't know, maybe if people are still watching this video in 30 years, they can get a 10% interest rate on a savings account. Here's hoping. And then they're telling us that this interest is compounded annually, which doesn't really mean a whole lot to us right now, but let me just fill you in on this whole compounding thing, because that's kind of important for this problem. When we have compound interest, it's basically interest on your interest. Just regular interest would just be like one time you get a 10% increase on the amount that you put in there. If you're compounding the interest, then the first year you increase this by 10%, and then the year after that you take the new total and increase that by 10%. And that's also including the interest from that first year. So it just keeps building, and this is actually a real thing. Based on all this, they want to know how much will be in your account after 8 years. So this seems like a different concept, but this is just kind of growth decay rate sort of stuff with some different wording going on. Pause the video and see if you can apply what we've seen so far to this situation. All right, so if we're choosing between growth and decay, fortunately, our account is growing in value, so we're going to go with growth. Again, we're using a times 1 plus r to the t. Our a value this time is our starting amount of money. That's this 700 here. We want to do 8 years, so we're doing f of 8 eventually when we plug things in here. And the r value is going to be 10% as a decimal, so we have 1 plus 0.1. And we're plugging in 8 for t, so that goes up there in exponent land. Let's put this in the calculator. So we have 700 times 1 plus, let's see here, 0.1 raised to the 8th power. And that is, we'll round it to 2 decimals because it's money. That's $1,500.51. All that just for leaving it in an account. That's kind of nice. For our final boss battle question here, we're going to talk about money again. That last problem was a nice little segue into this topic. On the last problem we saw, it was annual compounding, but this problem's a little bit different. So let's say we deposit $2,200, a little more than last time, we're working our way up here, into 3 separate bank accounts that each pay 3% annual interest. But they don't all do it exactly the same. Interest is compounded quarterly in account 1, monthly in account 2, and daily in account 3. And they want us to find the value of each account after 6 years. So how is this different from the last problem? Well, in the last problem where interest was compounded annually, that meant we basically figure out the interest once a year, and that's it. If you're compounding quarterly, that means we're essentially figuring out the interest and building on interest 4 times a year. And then monthly and daily even more so. So this is compounding multiple times a year. There is a way to do this kind of by hand, kind of all drawn out, but there's a formula that makes our lives much easier that we're going to introduce now. And then I'll explain kind of the intuition behind it. So this is the compound interest formula, and it goes as follows. The total amount in your account is going to equal P times 1 plus R over N, all raised to the NT. Now, what are all these letters? We've never seen any of these before, except maybe R. R is kind of familiar, and maybe sort of T. So this P here is the principal. That's the starting amount. That's what used to be the A value in the last few problems. The R is still going to be your interest rate. Again, that's going to be expressed as a decimal, so careful plugging that in. Now this N is a little bit different. This N is the number of times each year that we're compounding. So if it's annually, N is just 1, and this is just 1 plus R to the T power again, just our normal formula. But N could be more than 1. In this case, we've got some different values of N that we're going to be using. And then finally, this T here is another time value. This is the time length of the investment. Not the number of times we're compounding a year, the actual time that this investment is running for. So slightly different uses of time in this problem. Now the intuition behind all this is basically that you're taking your interest rate, chopping it into some smaller pieces, but then you're multiplying by this growth factor more times per year to kind of make up for that. So that's really what's going on here. We'll do the first account together just to kind of get the hang of this. So in account 1, we were compounding quarterly. So we have a principal, and this is going to be the same for all of them. We have a principal of $2,200. That's our starting amount. This 1 is going to always be a 1. Our interest rate was 3%, so that's going to be 0.03 in the fraction, and that's going to be the same every time. Now what's changing here is how many times we're compounding. If we're doing quarterly, that means we're doing this 4 times a year. So my n value down here is going to be 4. The n gets used again up here in the exponent, so we have a 4 up there as well. And then the time of the investment, they said 6 years. So we'll do 4 times 6. And needless to say, we're going to plug all that in using Desmos, not doing this by hand. So here we go, plugging it all in. We have 2,200 times parentheses 1 plus fraction 0.03 over 4. Close that parentheses, exponent button, and then we have 4 times 6. And that all comes out to approximately $2,632, and if we round it off, 11 cents. Cool. That's a decent amount of money there after 6 years on only 3%. So using this kind of idea, pause the video and using the different compounding rules here, see if you can figure out the amount in your account 2 and the amount in account 3. And we'll compare the numbers and see how much money we really get by compounding more than 4 times a year. All right, so let's check out account 2. Everything is going to be the same except that the n value here is going to be changing from a 4 to a 12 since there's 12 months in a year. So that's the only change. And this is an easy change to do in Desmos. Let me just go back in there and I'll just change out this 4 for a 12. This is awfully convenient. And now that changes our total to $2,633.27. So that was like almost over a whole dollar that you gained by doing it 12 times a year instead of 4. Let's do it daily now. Let's see how you did with daily. So daily, we're going to go with 365 days in a year. We're not going to worry about leap years. So that means our n value instead of 12 is now going to be 365. And let's go to Desmos and change that value again. So 12 becomes 365 down there, and up here 365 as well. And that changes our grand total to $2,633.86. So not a huge gain, but there is definitely some difference when you do more compounding. Most banks, when they're doing this interest in credit cards, use something called continuous compounding, which is basically like this on steroids. We'll actually get into that in our next lesson, but we're going to need to talk about the number e in order to make any sense of that. This seems like a good place to quit while we're ahead, though, on this one. So hopefully you found this lesson interesting. Until next time, this is Mr. Sutton signing off.